Okay, let's look at the change of variables. Alright, so let's use the change of variable given here to evaluate this double integral. Alright, so you can see that this double integral is fairly involved, and if you want to do it directly from here, we might have a hard time. So I'm going to use this suggested change of variable here. So instead of using x and y, I'm going to try to do it with respect to r and s and see if it's any simpler. Alright, so first we need to find Jacobians. Alright, so we just learned how to do find Jacobian. So it's so old variable is x and y, and we want to do it with respect to a new variable, and that's those are r and s. Alright, so let's do that. Alright, so we're gonna take the partial of x with respect to r, that will be 1/2, and the partial of x with respect to x s, that will be -1/2. Right, and partial of y with respect to r is +1/2, and the partial of y with respect to x is again +1/2. Alright, then so this is a determinant, so it's 1/2 times 1/2 is 1/4, and a minus -1/4, so it's going to be +1/4. Alright, so it came out to be 1/2. Right, so it is positive, so you don't really have to take the absolute value, so it's 1/2. Alright, so let's see which region we're integrating over. So here, maybe we should write this. This is going to be y equals x, and the y equals 1 minus x. So these are x values. So x goes from 0 to 1/2. Right? So y equals x. So that's just going to be a straight line through the origin with slope 1. Right? So this is y equals x. Right, to 1 minus x, so that would be, so y-intercept would be 1, so it's going to be up here, and a minus x, so slope is -1, so it's going down like that. Alright, so that's y equals 1 minus x. Alright, then we are going from, x is going from 0 to 1/2, and you can see that here, this is going to be 1/2 there. So here's 1/2, right? From 0 to 1/2, so we're talking about this region right here. So I'm going to show you, so this triangular region. Right, so that's the region we are talking about. Alright, so what we want to do is we want to translate that into, or transform it into the RS plane. So let's try to do that here. Alright, so I'm going to try to draw a new, in this case, R axis and S axis. So we're going to turn it into, so here's going to be a new picture. Right, so this is going to be our new R axis, and here's going to be our S axis, origin. Right, so let's look at each constraint. So let's look at this guy right here, y equals x. Right, so in terms of R and S, what does that mean? So we're basically equating those two guys together. So this gives us 1/2 r minus s is equal to 1/2 r plus s. Right? So we can cancel 1/2 and 1/2. So multiply both sides by 2, and we can subtract r from both sides. Alright, so it basically says that the negative s equal to s, or 2s equals 0. So this just means that s is going to be 0. Alright, so s equals 0 is simply just s axis actually, sorry, r-axis. So we're talking about these guys. So I'm going to just draw a line here, right? So that boundary is going to be transformed into basically the r-axis. All right. How about this guy right here? This constraint, right? We're going to go up here since there's more room. So I'm going to actually rewrite it as x plus y equals 1, right? So in terms of r and s, this is going to be equivalent to, so x is 1/2 r minus s, and a y is 1/2 r plus s, right? And this is going to be equal to 1, right? Then we can just simplify, right? So we can cancel, let's see, so you have a negative s here, positive s, they cancel out, right? So you basically have 1/2 s plus another half s equals 1, so which means that the r equals 1. So this just gives us r equals 1, right? So say 1 is going to be right here. So r equals 1 is just a vertical line here. Right? So that's the constraint there. And the last constraint here is this guy right here. Right? That's just the equation x equals 0. Right? So that would be just, I'm going to just say x equals 0. Alright, so this guy can be rewritten as, right, x equals 0. X is 1/2 r minus x is equal to 0. So we can multiply both sides by 2. So this just basically r equals s, or s equals r. Right? So that's going to be just slope 1 going through the origin of the rs plane. So this is s equals r, right? So we know that this is 1, and looks like here this is going to be 1 as well. So translated region, I'll probably shade it here. So this is going to be the new region we want to integrating over. Right? Right. So remember that the absolute value of Jacobian kind of gives you the like a expansion rate. So if you use the change of variable, the region is going to be, you know, transformed into a different region. Of course, it's going to expand or contract. So J is going to actually takes care of that. Right. So here it's equal to. So it's still going to be a double integral. Right. Then here, so you have a x minus y. So x minus y would be, so you have x, so 1/2 r minus s minus 1/2 r minus s. So 1/2 r will cancel out. So it's going to be a negative 1/2 s minus 1/2 s. So it's going to be negative s. So negative s on top. Right, x plus y. X plus y is going to be, if you add them up, s's cancel out, so you're going to have 1/2 r plus 1/2 r, so you're going to have r. Right, so we can rewrite x plus y as negative s, x plus y as r. Then we will still have to square this guy. Right, then we have to use a j, which is 1/2. Then we can use the, you know, d, let's see, which one should we do? ds first, dr. All right. So then you can focus on the upper, lower bounds and upper bound. So fix r. So we are fixing r. So let's say we're gonna fix r. So I'm gonna just, here's my fixed r. Then you can see that the s is going to start from, this is s equals 0, right? Then go all the way to s equals r, right? So we know that this is going to be s equals 0 to s equals r, right? Once you've done that, r value is going to start from here, which is r equals 0, and then you go r gradually increases, and to cover the entire triangular region, we're going to go all the way up to r equals 1. So here we have r equals 0 to r equals 1, right? So that's the new integral, and cross our fingers that this is going to be a little bit simpler. All right, so let's do that. All right, first, so since we're doing with respect to s, everything else is going to be treated as a constant. So I'm going to leave r equals 0 to r equals 1, right? And also, let's see, r squared on the bottom and a 1/2. So it's a 1/2 r squared is left alone. And then we take the antiderivative, basically s squared. So that will be s cubed, just the power rule, s cubed over 3. Then you're going from, s is going from 0 to r, right? Then we still have to do with respect to r, right? So this is going to be equal to, right? So it's an integral from r equals 0 to r equals 1. We still have 1/2 r squared. Then if you plug in r, so you have a r cubed over 3. If you plug in 0, it's 0 anyway, so I'm not going to write that down. And we have a dr. Alright, so we can cancel. So there's r squared here, and there's r cancel out. So there's going to be r squared cancel out. So there's going to be still r left. So if you take the antiderivative of that, you're going to get r squared. And you have 2 and 3, so 6, and then divide by 2, so it's 12. Then you're going from 0 to 1. Oh, actually, I messed it up here. So this is supposed to be 1. Right? Then this one's easy. Plug in 1, you get 1 squared over 12 minus 0 is 0. Right? So the integral, the value of the double integral came out to be 1 over 12. And this is done using the change of variable. So it makes our life so much easier using this clever change of variable to simplify this fairly complicated double integral into a very simple double integral. It's all power rule. Alright, that's it. I hope that this was clear.